Docker machine? Well, like Docker machine, it's a cluster manager for Docker. It contains everything you need, such as orchestration, service discovery, load balancing, and more. So it has a little bit more built into it than Docker machine currently does in its related components. That's one nice thing about it. And it was originally made for Google Cloud Engine, but you can bring it anywhere. It has documentation for running on AWS and other providers as well. And unlike Docker Machine, Docker Swarm, and the Docker suite of tools, Kubernetes attempts to bring in new concepts because they didn't believe that vanilla containers were enough. Some of these we'll be going over later include things like pods, services, and replication controllers. Many of these have metaphors and are related to some of the things that we've learned about Docker Swarm, but many of them don't really directly carry over. So first off, like Docker Swarm, it works on a master and minion architecture, or nodes as they like to call them. One master oversees and manages your Kubernetes node machines. Currently, there is a single master and all components are on it, so it's a single point of failure. However, there are plans in the not too distant future to make masters highly available and distributed to resolve this scenario. Kubernetes minions run tasks provided to it by the Kubernetes master. So your Kubernetes master is separate from all your processing tasks run by your minions. You cannot have both running on the same machine. As an implementation detail, Kubernetes uses etcd to facilitate communication between the masters, nodes, and all the different components. Additionally, Kubernetes is built on top of etcd to facilitate key value pairs and labels across your different components in Kubernetes. As we'll see, you can apply labels to each Kubernetes construct, and there's many different use cases for this, similar to labels for Docker Swarm. So the first construct introduced by Kubernetes is something called a pod. Pods are groups of Docker containers meant to represent some specific type of application. They're the most basic unit in Kubernetes, and when working with Kubernetes, you should no longer think at the container level, you should start thinking more at the pod level. All containers that are part of the same pod are meant to be collated together. And this is a major change in design philosophy because many felt that the container wasn't a powerful enough abstraction method. So the way that you'd actually use these more or less is if you had a traditional application or two different components would need to run on the same physical machine or virtual machine, in the Kubernetes world, these would be part of the same pod. So let's say that you had a main backend server and some sort of worker process that was very tightly coupled to it and should be running on the same machine as it. You would put these together inside the same pod definition instead of putting them in the same container. This allows you to have the best of both worlds where you can get the nice clean dependency manager brought to you by containers, while at the same time recognize this necessary dependency that they have between each other. While you can directly create pods, this isn't the recommended way to do it. Instead, Kubernetes recommends using something called replication controllers. What replication controllers are, abstractly speaking, a construct that creates or replicates pods for you. One of the main facilities created by replication controllers is ensuring that a specified number of pods are running. Let's say that you were to natively fire off 3 groups of pods. If something were happening to these pods, such as the node going down or any sort of other issues, pods don't have any way to self-heal. Instead, though, if they were created by a replication controller that's saying, okay, always make sure that we have 3 of these running, it will spin up new pods to compensate for this. It'll make sure that all these pods are running across all the different machines. So if you have one machine go down that's carrying 2 of your pods, it'll just move that workload over to another machine. In addition to this, it'll also make sure that you have exactly that number of pods running. So if for whatever reason you accidentally get 5 pods instead of 3, it'll kill off 2 of them. Another key feature of replication controllers is you can use them for rolling updates. It's a great way to kill off the old pods and bring up new ones when you do an application update. So these pods are loosely coupled from the replication controller. The only link between them after creation is a label, which we'll discuss shortly. The way that Kubernetes decides in their documentation is replication controllers are like a cookie cutter and the pods are like cookies. After they're created by the controller cookie cutter, they're their own separate entity that can be managed on its own. Another abstraction introduced by Kubernetes is the idea of services. Kubernetes services act as sort of endpoints and load balancers, and they allow users to only concern themselves with one access point. Specifically, a service will sit in front of a group of replicated pods and distribute traffic to them. When properly configured, pods created by the replication controller will automatically register with an appropriate service. The idea behind this is each pod is assigned its own IP address, and this is dynamically assigned. So let's say that you have a collection of front-end pods that represent the front end of your website and a collection of back-end pods that represent the back end of your website, and they had to communicate with each other. Without services, you would have to register the individual IPs and manage what would happen if something were to go down. It'd be very brittle to individually link all these front ends and back ends together because pods, like containers, are ephemeral and can go down at any time. So instead of going through all that, you can hide a group of the same pod together behind a service to allow other pods and your end users to communicate with them through one endpoint. And as mentioned earlier, a lot of this is implemented through labels, which are arbitrary tags that can be used for other work units. They're integral to the way that replication controllers and services operate, because as mentioned earlier, replication controllers will attach a label to each pod that they generate, and units can have more than one to define application topology.